In this video, I'll be going through the 2021 May-June A-Level Physics Structured Questions paper. The Earth may be assumed to be an isolated uniform sphere with its mass of 6.0 times 10 to the 24 kilograms concentrated at its center. A satellite of mass 1200 kilograms is in a circular orbit about the Earth in the Earth's gravitational field. The period of the orbit is 94 minutes. Define gravitational field strength, which is gravitational force per mass. Calculate the radius of the orbit of the satellite. To do this, we first need to recognize that the centripetal force is provided by the gravitational force. Substituting their respective equations, we can divide out our little mass, which is the mass of our satellite, and multiply both sides by r to cancel out this r and cancel out this exponent. We know that velocity is distance over time, where we know that the satellite travels one circumference, which is 2 pi r, in our time, our period. Substituting this into our v, multiplying both sides by r, and now dividing both sides by 2 pi squared, multiplying it by t squared, and then taking the cube root. Putting our numbers in, where our period is 94 minutes, which is 94 times 60 seconds. Which gives me 6.86 times 10 to the 6 meters. Rockets on the satellite are fired so that the satellite enters a different circular orbit that has a period of 150 minutes. The change in the mass of the satellite may be assumed to be negligible. Show that the radius of the new orbit is 9.4 times 10 to the 6 meters. We can reuse our equation right here, where instead of 94 minutes, we substitute our 150. Which gives me 9.36 times 10 to the 6 meters, which to two significant figures is what we're trying to find. State with a reason whether the gravitational potential energy of the satellite increases or decreases. It increases because the satellite has moved against the gravitational field. Determine the magnitude of the change in the gravitational potential energy of the satellite. Our change in energy is going to be the difference between the gravitational forces multiplied by their respective radiuses. Substituting our gravitational force equation, simplifying by cancelling our radius in our numerator with the power in the bottom, and also factorising out our GMM. Putting our numbers in, gives me negative 1.85 times 10 to the minus 10 joules. An ideal gas is contained in a cylinder by means of a movable frictionless piston, as illustrated in figure 2.1. Initially, the gas has a volume of 1.8 times 10 to the minus 3 meter cube at a pressure of 3.3 times 10 to the 5 Pascal at a temperature of 310 Kelvin. Show that the number of gas molecules in the cylinder is 1.4 times 10 to the 23. Recalling our ideal gas equation, PV equals nKT, solving that for n by dividing both sides by kT, and now putting in our numbers. Where K is Boltzmann's constant, which you can find on the formula page. Which gives me 1.39 times 10 to the 23, which to two significant figures is what we're trying to find. Use kinetic theory to explain why, when the piston is moved so that the gas expands, this causes a decrease in the temperature of the gas. When molecules strike the moving piston, they lose kinetic energy. Because temperature is proportional to the kinetic energy of the molecules, the temperature decreases too. The gas expands so that its volume increases to 2.4 times 10 to the minus 3 meter cube at a pressure of 2.3 times 10 to the 5 pascals and a temperature of 288 Kelvin, as shown in figure 2.2. The average translational kinetic energy, EK, of a molecule of an ideal gas is given by this equation here, where K is the Boltzmann constant and T is the thermodynamic temperature. Calculate the increase in internal energy of the gas during the expansion. The change in internal energy is going to be the difference between the final and initial kinetic energies. and because this equation is the kinetic energy of a molecule, we need to multiply it by the amount of molecules. Factorizing out our 3n k/2, putting in our numbers, where our n is our amount of gas molecules here, which gives me negative 63.8 joules. The work done by the gas during the expansion is 76 joules. Use your answer in I to explain whether thermal energy is transferred to or from the gas during the expansion. To perform this expansion, our gas needed 76 joules of energy. Because our gas only lost 63.8 joules of energy, energy must have been transferred to the gas to make up for this shortfall. The expansion required 76 joules of energy. Because the internal energy of the gas only reduced by 63.8 joules, energy must have been transferred to the gas to make up the difference. State what is meant by simple harmonic motion. This is motion where the acceleration is proportional to and opposite displacement. A trolley of mass m is held on a horizontal surface by means of two springs. One spring is attached to a fixed point P, the other spring is connected to an oscillator as shown in figure 3.1. The springs, each having spring constant K of 130 newtons per meter, are always extended. The oscillator is switched off, the trolley is displaced along the line of the springs and then released. The resulting oscillations of the trolley are simple harmonic. The acceleration a of the trolley is given by the expression here. Where x is the displacement of the trolley from its equilibrium position, the mass of the trolley is 840 grams. Calculate the frequency f of the oscillation of the trolley. You might recall that a is negative omega squared x, which means that our 2k/m is equal to omega squared. You may also recall that omega is equal to 2 pi f, so we can make that substitution. Solving for f by dividing both sides by 2 pi squared and square rooting, and putting our numbers in, which gives me 2.8 Hz. The oscillator in B is switched on, the frequency of the oscillation of the oscillator is varied, keeping its amplitude of oscillation constant. The amplitude of oscillation of the trolley is seen to vary. The amplitude is a maximum at the frequency calculated in B. State the name of the effect giving rise to this maximum. The effect is called resonance. At any given frequency, the amplitude of the oscillation of the trolley is constant. Explain how this indicates that there are resistive forces opposing the motion of the trolley. Since the system is driven, energy is being added. Because the amplitude isn't increasing, neither is the energy. Energy must therefore be lost to resistive forces. Outline the use of ultrasound to obtain diagnostic information about internal body structures. Sound waves are directed into the body. A gel is used at the surface to reduce reflections. When the sound waves encounter a difference in refractive index, they partially reflect. The greater the difference, the more intense the reflection. By observing the duration between emission and detection, the depth of the reflection can be determined. State what is meant by amplitude modulation of a radio wave. The signal is communicated through variations in amplitude. A radio is modulated by an audio signal. The variation with frequency of the amplitude of the modulated wave is shown in figure 5.1. Determine the wavelength of the carrier wave. We know that the wave speed is equal to frequency times lambda, solving this for lambda by dividing both sides by frequency, putting our numbers in, where our frequency is 300 kHz, giving me 1000 meters. Calculate the bandwidth of the modulated wave. The bandwidth is the width of this band here, which gives me 16 kHz. Calculate the maximum frequency of the audio signal. The maximum frequency is the difference between our middle frequency and the upper and lower range, which is 8 kHz. The power of a radio signal at a transmitter is Pt. At a receiver, the received power Pr is given by the expression here, where x is the distance in meters between the transmitter and the receiver. For the transmission of the signal, the attenuation is 73 decibels. Determine the distance x. Our attenuation is 73, And attenuation is equal to 10 log 10 of the power transmitted divided by the power received. Dividing both sides by 10, substituting for PR, and we'll continue down here. Simplifying this down by dividing out our PT, and because x squared is a denominator in a denominator, it moves up to the numerator. We now need to solve for x. To solve for something in a log, we need to remember the definition of a log. A log 10 is asking 10 to the power of what is equal to x squared over 0.082. Once again, this is just the definition of a log. Solving for x squared by multiplying both sides by 0.082, square rooting both sides and swapping them around, gives me 1280 meters. An isolated metal sphere of radius r is charged so that the electric field strength at its surface is E0. On figure 6.1, sketch the variation of the electric field strength E with distance x from the center of the sphere. Your sketch should extend from x equals 0 to x equals 3r. The radius of our sphere is r, so that everything less than r is within our sphere, within which the electric field strength will be 0. Knowing that at our radius r the electric field strength is E0, we know that we have a point up here, and because our surface is a sphere, this is governed by the inverse square law. So if we multiply our radius by 2, our field strength is going to decrease by a factor of 1 over 2 squared, which is 1 over 4. We have 6 of these large boxes. A quarter of 6 is 1.5. Increasing our distance by a factor of 3 is going to see a reduction of 1 over 3 squared, or 1 over 9. 6 over 9 is 2 over 3, which is around about 0.6. The de Broglie wavelength of a particle is lambda naught when its momentum is p naught. On figure 6.2, sketch the variation with momentum p of the de Broglie wavelength lambda of the particle for values of momentum from p naught over 2 to p naught. So we know that our de Broglie wavelength is Planck's constant over p. We're told that at lambda 0 we have p naught, so we can mark that point. If we have p naught over 2, from our equation here, if we halved our momentum, we're going to see a doubling of lambda. So we can mark that point. Furthermore, we see that the relationship between lambda and the momentum is an inverse relationship, meaning that it's going to look like this. A radioactive isotope decays with a half-life of 15 seconds to form a stable product. A fresh sample of the radioactive isotope at time equals 0 contains N0 nuclei and no nuclei of the stable product. On figure 6.3, sketch the variation with T of the number N of nuclei of the stable product for time t equals 0 to time equals t equals 45 seconds. Because this is the number of our stable product, at time equals 0, we're going to have 0. Because we have a half-life of 15, after 15 seconds, half of our nuclei will have decayed to our stable nuclei. So after 15 seconds, we're going to have 0.5 times N0. After another half-life of 15 seconds, half of the remaining nuclei will have decayed, adding their ranks to our stable nuclei. After another 15 seconds, we will once again gain half of the difference. State what is meant by the capacitance of a parallel plate capacitor. Capacitance is the charge stored per volt applied. A capacitor of capacitance C is connected into the circuit shown in figure 7.1. When the two-way switch is in position A, the capacitor is fully charged, so that the potential difference across it is V. The switch moves to position B, and the capacitor fully discharges through the sensitive ammeter. The switch moves repeatedly between A and B, so that the capacitor charges, and then discharges with the frequency F. Show that the average current I in the ammeter is given by the expression I equals FCV. The equation for capacitance is charge over voltage, and current is charge over time. We can solve both of these for charge, where t is the period of our charge, and because period is 1 over frequency, we can make that substitution. Setting these equal to each other, multiplying both sides by f, we arrive at the equation we're trying to find. For a potential difference of 150 volts and a frequency of 60 Hz, the average current in the ammeter is 4.8 microamps. Calculate the capacitance in picofarads of the capacitor. We know from earlier that I is equal to FCV, solving that for capacitance by dividing both sides by FV. We know our current, we know our frequency, and we know our voltage, where micro is times 10 to the minus 6. Which gives me 5.33 times 10 to the minus 10 farads, which because pico is times 10 to the minus 12, to write this in picofarads, we need to move our decimal point 2 places, giving me 533. A second capacitor having the same capacitance as the capacitor in B is connected into the circuit of figure 7.1. The capacitors are connected in series. State and explain the new reading on the ammeter. The equation for capacitors in series is 1 over the total is equal to the sum of the 1 over capacitances. This is opposite to resistors. 1 over C plus 1 over C is 2 over C. Taking the inverse of both sides, we see that our capacitance has halved. Looking at this equation here, if we halved our capacitance, we must also halve our current. So our current must be 2.4. C is halved. Since I equals FCV and F and V are constant, I must also halve. The variation with temperature of the resistance of a thermistor is shown in figure 8.1. A student includes the thermistor and an ideal operational amplifier in the circuit of figure 8.2. Calculate the potential V plus at the non-inverting input of the op-amp, where our negative terminal is our inverting terminal and our positive is our non-inverting. Because we're asked for the potential at the non-inverting input of the op-amp, we're looking for this voltage here, the voltage across our 3 kilo ohm resistor. We know that V is equal to IR, where we know that our resistor is 3 kilo ohms, but we don't know our current. To find our current, we can also use V equals IR, solving for current by dividing both sides by R, where our current through our 3 kilo ohm resistor is the current through this path here, equal to our voltage of 3 divided by our total resistance, which because these two resistors are in series, is their resistances added together. Substituting that into our equation over here, where I'm able to ignore the kilo because we have kilo ohms down here and kilo ohms up here, so they essentially cancel out, giving me 1.64 volts. At 10 degrees Celsius, the resistance of the thermistor is 2.5 kilo ohms. State and explain whether the light emitting diode is emitting light. If our resistor is 2.5 kilo ohms, then we can find our voltage by considering that our current is going to be the voltage of 3 divided by the total resistance, which is going to be 2.5 plus 5, and because the voltage at our inverting input is the voltage across our 5 kilo ohm resistor, we use our 5 kilo ohm resistance. What we're doing is basically the same as last question. That gives me 2 volts. V minus is greater than 1.64 volts at 2 volts, the output is therefore negative, the LED is reversed biased, and therefore will not glow. Explain why the student circuit will not indicate any change in temperature above 0 degrees Celsius. At 0 degrees Celsius we have a resistance of 3.8 kilo ohms, which if we use this equation here, which gives me 1.7 volts. At 0 degrees the thermistor is 3.8 kilo ohms and the inverting output is 1.7 volts, greater than the non-inverting. Reducing the temperature further will increase this voltage and the LED will remain dark. The resistor of resistance 5 kilo ohms is changed to a resistor of resistance R so that the LED switches on or off at a temperature of 20 degrees Celsius. Determine R in kilo ohms. So our 5 kilo ohm resistor is now some resistance R that we're trying to find, and at 20 degrees, our thermistor is 1.8 kilo ohms. At the point where our LED switches on or off, our voltages must equal. Substituting V equals IR, where for R1 our resistance is 3, and for R2 our resistance is R. That's because our non-inverting input is across our resistor of 3, and our inverting is across our resistance of R. Now we know that V is equal to IR, and I is equal to V over R, and we know that our respective currents are the voltage across our entire branch, which in both cases is 3 volts, divided by the total resistance of that branch, which for our first branch is 2.5 plus 3, and our second branch is 1.8 plus R. 2.5 plus 3 is 5.5. Dividing out a 3, solving for R by multiplying both sides by 1.8 plus R, and also swapping them around. Expanding out our brackets. Subtracting 3 over 5.5 R from both sides. Factorizing out our R. And dividing both sides by our brackets, which gives me 2.16 kiloohm. State what is meant by a magnetic field. A magnetic field is a region where a moving charge experiences a force. A rectangular piece of aluminium foil is situated in a uniform magnetic field of flux density B, as shown in figure 9.1. The magnetic field is normal to the faces PQRS of the foil. Electrons, each of charge negative Q, enter the foil at right angles to the face PQTV. On figure 9.1, shade the face of the foil on which the electrons initially accumulate. For this, we can use the right-hand rule to determine the direction of the force on the electrons. Take your right hand and point your fingers downwards with the magnetic field. Your thumb then points in the direction of positive charge movement. So because we have negative, your thumb will point in the opposite direction to the movement of the electrons. Doing this, your palm is going to point towards the surface PSVW. Explain why electrons do not continuously accumulate on the face you have shaded. As charges accumulate, they establish an increasing electric field that applies a force to incoming charges. When this force equals the magnetic force, the charges stop accumulating. The Hall voltage developed across the foil in B is given the expression this, where I is the current in the foil. State the meaning of the quantity N. N is the density of charge. Using the letters on figure 9.1, identify the distance T. The distance T refers to our distance along here, so we could say QT, PV, or SW. Suggest why in practice, Hall probes are usually made using a semiconductor material rather than a metal. Semiconductors have a smaller charge density. Since VH equals BI over NTQ, VH is larger. State Lenz's law. When a changing magnetic flux induces a current, the direction is such that the magnetic field of the current opposes the change. A metal ring is suspended from a fixed point P by means of a thread, as shown in figure 10.1. The ring is displaced a distance d and then released. The ring completes many oscillations before coming to a rest. The poles of a magnet are now placed near to the ring, so that the ring hangs midway between the poles of the magnet, as shown in figure 10.2. The ring is again displaced a distance d and then released. Explain why the ring completes fewer oscillations before coming to a rest. When the ring swings, it experiences a changing magnetic flux, causing currents to be induced in it. The magnetic field from these currents opposes the field of the magnet, causing the ring to experience a force in opposition to its motion, slowing it down. The ring in B is now cut so it has the shape shown in figure 10.3. Explain why when the procedure in B is repeated, the cut ring completes more oscillations than the complete ring when oscillating between the poles of the magnet. As the ring is cut, current is no longer able to flow continuously within it, reducing the resistive force. State how in a modern X-ray tube, the intensity of the X-ray beam and its hardness are controlled. The intensity is changed by changing the current, more intensity. And hardness is changed by changing the voltage, more hardness. A model of a limb consists of soft tissue and bone, as illustrated in figure 11.1. The soft tissue has a thickness of 9 cm. The bone within the soft tissue has a thickness of 3 cm. Data for the linear attenuation or absorption coefficient of X-rays in soft tissue and in bone are shown in Table 11.1. A parallel beam of X-rays of intensity I0 is incident normally on the model. Calculate in terms of I0 the transmitted intensity Is through the soft tissue alone. The intensity is given by I0 times the exponential of negative mu times x, where if we're looking at the soft tissue alone, we're looking at a x of 9 cm and a coefficient of 0.92. Which gives me 2.54 times 10 to the minus 4 I0. Calculate in terms of I0 the transmitted intensity IC through soft tissue and bone. Recalling that we have our soft tissue with our bone in the middle, where our soft tissue has an attenuation of 0.92 and our bone of 2.9. As for our distances, we know that this entire length is 9 and our bone is 3, which means we must have 3 on either side, meaning that all 3 sections are 3 cm. Now for our intensity, that's going to be I0 multiplied by the exponential for this section, multiplied by the exponential for this section, multiplied once again by the exponential for this section, which gives me 6.67 times 10 to the minus 7 I0. By reference to your answers in B, suggest with a reason whether good contrast on an X-ray image would be obtained. Comparing our two intensities, we see that IS is much larger than IC, so we could expect good contrast. IS is much larger than IC, so we can expect good contrast. Electromagnetic radiation of a single constant frequency is incident on a metal surface. This causes an electron to be emitted. Explain why the maximum kinetic energy of the electron is independent of the intensity of the incident radiation. The maximum kinetic energy depends on the energy of the incident photons. Increasing the intensity will only increase the amount of photons, and therefore the amount of ejected electrons. Ultraviolet radiation of wavelength 250 nanometers is incident on the surface of a sheet of zinc. The maximum kinetic energy of the emitted electrons is 1.4 electron volts. Determine in electron volts the energy of a photon of the ultraviolet radiation. Photon energy is equal to Planck's constant times the frequency, where although we don't know the frequency, we do know that c is equal to frequency times lambda, and we know c is 3 times 10 to the 8, and we know lambda, which is over here. Solving that for frequency, and now substituting it into our equation, putting in our numbers, gives me 7.96 times 10 to the negative 19 joules. Dividing that by the charge of the electron gives me 4.97 electron volts. Determine in electron volts the work function energy of the surface of the zinc. The energy of our photon is divided into the energy required to liberate it from the zinc, which is our work function that we're trying to find, plus its leftover kinetic energy. We know the energy, we just found it over here, and we know the kinetic energy, we were given it above. Solving that for work function, putting our numbers in, gives me 3.57 electron volts. And we're done.